materials, meaning that they are ordered, they have ordered structure, and their structures have been characterized and are characterized by single crystal X-ray diffraction. And if you zoom in to the eye, they appear like granulated sugar. If you zoom in on one granule, you will see their beautiful network-like structures made from intersections or hubs that are inorganic, linked by organic to make open structures into which our idea is to compact gases just like bees on a honeycomb. Bees may fill very large volume, but if you have a piece of honey, which could be the MOF, they assemble around that and compact them, compact gases such as hydrogen, CO2, or water without having to use pressure or low temperature. And so that's the idea with MOFs. And well, almost any element metal in the periodic table has been used to make a MOF. The metals make metal oxide units that they are then joined by organic units, and the organic units could be as simple as lactic acid, which is in milk, citric acid in orange juice, or petroleum-derived clinkers such as terephthalate and so on. And they could be as small or as long as this one, where you could make MOFs that would take the proteins in, or they can have very exotic shapes, but each imparting a different property, whether it's a photophysical property or a catalytic property, onto the framework. So the other powerful thing about MOFs is that since you can adjust which building units you're using, you could also adjust the metrics of the pores. You could make small pores or larger pores, and here's a great student who didn't stop after making the first and second one, kept going and made the largest pore material ever accessed in crystalline form. And as I said, these can have they can also incorporate biological molecules, making them interesting for biotechnology applications as well. So it's really, we created almost a periodic table of reticular compounds, and the challenge is, is trying to figure out what you want to make. And if you do, you can combine shapes on this side with this side, and this table will tell you what you're going to make. And almost 90% of the time, this is correct, which is much better than any other chemistry. And the reason is that these geometric building units do not undergo changes during the assembly process, so you can actually predict how they are going to come together. And you can see all kinds of shapes on this side. Molecules can have triangle, square, tetrahedron, and so on and so forth, and you can combine them with other molecules. These could be inorganic, these could be organic. You know, the amazing thing about MOFs is that, let's say I make this structure out of triangles. I could spend my whole life working on this, and not only because it has a rich chemistry itself, but also because I can adjust all the metrics. I can make larger units, functionalize those units, make catalysts, make carbon capture materials, and so on. So each one awaits a long chemistry that would be developed. And well, you can also combine those shapes with more complex shapes, and you can keep going, right? And some of the younger people in the crowd don't feel despair. There's still a lot of work to be done, especially when it comes to the complex shapes. So what I want to say here is that if you can think it, we can make it. Okay? It took us 35 years to develop the chemistry. And the reason I'm interested in AI, and I collaborate with Jennifer and Christian extensively as part of the Bitmap Institute, is that when you assemble these building units, the very first thing a student experiences is that they're not highly crystalline. And so they spend 2 to 3 years doing trial and error in terms of finding the conditions under which to crystallize them. That's where AI is becoming really, really important. And so very early on, we showed that these can be made in multi-ton quantities in our collaboration with BASF. They can be made cheaply and all the things that you need. So what I want to talk about today is what we've done in what I call the air economy, which is carbon capture, water capture from air. You can get hydrogen from water. That's Peidong will talk about that. We already take oxygen out of the air, and we also take nitrogen out of the air to make fertilizers. So today I want to show you two examples of carbon capture and water harvesting. Okay, so the best CO2 capture material from air is here, and it's a COF. It's not a MOF. It's actually an all-organic material called covalent organic frameworks, where the constituents are linked by some of the strongest bonds known in chemistry, carbon-carbon double bonds and carbon-nitrogen double bonds. It took us over 10 years to figure out the chemistry of this framework, but now we can make it routinely and in high yield. We can functionalize it with those amines that Jeff Neaton was talking about to trap CO2. And this is the experiment that convinced me that there will be life on our planet, that we can capture the CO2 that's causing climate havoc. And that's this experiment. Here's the CO2 concentration, Berkeley air. It's around 450 ppm. This is the humidity level, and this is the material taking up CO2 from the air. And you can, when you pass Berkeley air into the solid or into the powder of this COF, it traps all the CO2 that's in the air. You get no CO2 on the other side of the material. That's how effective it is, and we find a relationship between water and the CO2 uptake. The more humidity in the air, the better the uptake. But when you look at one humidity level, the behavior is constant throughout the experiment. This is the best performing carbon capture material for air capture, for CO2 from air, that has ever been reported, and these are the parameters that convince anyone that this is commercializable. So at scale, we want to take the 1,100 gigatons of extra CO2 from the air, and using our material, this is the parameters, this is capacity is 2 millimole of CO2 per gram of COF, and each cycle takes 10 minutes, CO2 in and then CO2 out, that's one cycle. And to get this job done using this COF, if you have a plant that deploys 100,000 tons of COF, it will capture half a gigaton of CO2, okay? But if you have 700 plants or so in cities around the world that have a population of 1 million or more, it will take us only 3 years or so to take away all that extra CO2 out of the air, okay? And then, you know, I mean, that's your quanta. You can divide it in the way you want. If you want just 200 cities that are 2 million or greater in China, US, and Europe, it'd be 11 years. It's doable. And what's convinced me that it's doable, not just that the properties that we have obtained and the stability of the material, but also that the chemical industry is used to this kind of scale. I mean, the world produces globally 200 million tons of sulfuric acid. Okay, COFs are a lot safer than sulfuric acid. They're solids. They're non-volatile solids. So we have the chemical industry, we have the ability to work on that scale. And so I think the carbon capture problem is solved. Scientifically it's solved. It just needs the will of society to say this is a crisis that we want to invest in. Okay, I think for water capture, I'm going to skip it, but we can make MOFs that take up water from the driest of deserts and make drinking water, okay? With no energy input aside from ambient sunlight. And the water is pure, it's clean, and the MOF not only works at dry desert, if it works in this case in Death Valley, it will work in Singapore. Okay, it will work at all humidity levels. In places where you might have a lot of humidity, but the water is not clean, you could use it also to trap water from not just arid but humid areas. And for the water harvesting from air, these are where we are. 1 ton of MOF with no energy input aside from ambient sunlight will give you 3,000 liters of water per day, every day, for about 6 to 7 years, for the lifetime of the electronics of the device, okay? And if you want to electrify it, it's 60,000 liters of water per day, every day, for 6 to 7 years. So this is, again, another problem that we are addressing, and it looks pretty impressive and close to commercialization. Okay, so I want to share with you, this is the sort of the main point that I want to communicate with you today concerning the use of AI for discovery of new materials and for optimizing properties. And this is a result of 2 years of work and collaboration with my colleagues, Christian, Jennifer, and postdocs that are working in BitMap. We have, you can think of it as 2 cycles. One is AI computational cycle, and the other one is experimental cycle. And typical chemist will input either a chemical formula, you have building blocks, they have chemical formulas, or a desired property that you want, maybe CO2 capture. And using this generative model based on diffusion models, you can get some initial structures. Many of them, hundreds of thousands, can be generated. And I'd like to say that Teo is really in charge of this project. He's a BitMap fellow. And you get hundreds of thousands of structures. Some of them are not so chemically viable. These are weeded out by doing a quantum level kind of geometry optimization like DFT and ML machine learning force field. You get your optimized structures, but then you do even more. You try to weed out the structures that are not going to be porous, since we are looking for porous structures if we are trying to do CO2 capture. And this involves Monte Carlo sampling, a machine learning type predictor, and ultimately a human check. Then using this, we get out some synthesizable structures. Okay, synthesizable structures have gone through, are the building units available? Are they widely available? Are they cheap? Do they require dangerous solvents to make, or can we make them in benign solvents? So all of that can be incorporated into this input. And this gets picked up by an LLM that does the synthesis planning, as was described by Gabe earlier. And this synthesis planner gives you, in our case, we're looking for conditions under which you could crystallize the material. And like I said, crystallization is 90% of our time as chemists is spent trying to crystallize our compound. And it's one of the most long-standing problems in chemistry. So it will spit out some reaction conditions. This could be temperature, solvent type, all those things. And so we subject it to an automated synthesis using robotics, high throughput, and we ensure that, in fact, what we make is reproducible. So we take extra care to make sure that every time you do this, based on those specific conditions, that you'll be able to do it, because later we want to scale it up. Then you have some synthesis outcome crystals, and we use multimodal characterization using automated imaging, X-ray diffraction, spectroscopy, some technique that we can automate, and then we get our characterization data. This is then subjected to an ML-assisted data analysis to recognize the crystals, to identify the phase in crystallography, assign spectra, and now you've got your potential good structure, okay? We compare this to what we have targeted back here in our synthesizable structures. And if it's good, if it's satisfactory, then we go to a property. We say, okay, now I've got my structure, can it do this or that? And if that's satisfactory, then this is more measurements, right? To check whether the material has the properties you need. That would be your platform output. If it's not satisfactory, then you put it in the data set and you go through the cycle again. Okay, and so using this kind of AI computational experimental combination is quite powerful, because you get to put in the good data and the bad, and the experiments that didn't work, the things that's all embedded in the cycle. So what's the result of this? The result is that we chose a subclass of MOFs called ZIFs. Never mind what they are, but they're basically zeolites that are made from metal organic. Our initial data set was about 2,600 reactions. We used 8 different linkers. And the result of this was that our discovery rate was twice that of my lab, okay? So you can think of this in the following way, that for the last almost 20 years, people have been making ZIFs, okay? And they made, 200 ZIFs. And we can do double that in less time, okay? So, and some of these structures are obvious in the art, meaning that I would look at them and say, oh, okay, they're new, but I could have guessed. But some others are completely new that I wouldn't have been able to guess. And they're very interesting for applications such as separating alcohol from water, which is a very difficult thing to do because they're azeotrope. The other result was that based on those cycles, you can come up with some sort of exotic linkers that we haven't thought about. And maybe they will lead to a new class of materials that I call hypoorganics, where you have the least amount of CH bonds per linker. These hypoorganics are emerging as very, very interesting for carbon capture. One of them is already capturing carbon dioxide from the air, not from the air, but from cement plants in Canada, and it's being commercialized. So using those, the students are able to get those linkers that were put out by those cycles and actually use the experimental cycle to make the corresponding MOFs. In no time at all, within 1 week, the students were able to get them in crystalline form. So that's the kind of transformative thing that's happening in the way we do chemistry in my lab. The things that have been taking years are taking weeks. And somebody mentioned already LLMs, and we have been experimenting with ChatGPT, and my students have done and published work on using LLMs, text mining. We're among the first to do this in the chemistry community. They are some of the most highly downloaded papers in chemistry. But today I want to focus on the research group as a last example. I know I have 1 minute left. So here's a typical activity in my lab and in general in chemistry. That is, you imagine a structure. We imagine this structure. It's a cough, and we deemed it interesting for potentially harvesting water from air. Okay, it has hydrophilic centers, hydrogen bond donor to water, and lone pair acceptor to water. So I'm sorry, I should have said hydrogen acceptor and hydrogen donor. So it would take my students, who are absolutely brilliant, okay, it would take them 2 to 3 years to crystallize this material. They may be making it in 5 minutes, but to actually make it in crystalline form, it would take them 2 to 3 years. And using ChatGPT as a multi-agent ChatGPT that does a lot of the stuff, like read the literature, summarize the literature, guide. This is the PI, guiding the experiment, analyze, synthesize, do the programming of the robot, and so on and so forth. Do the 3D printing of the glassware or the materials that we use for the experiment. And in doing this, the student is able to go from a non-crystalline material to a crystalline material in the course of about 84 experiments. Okay, using the cycle that I have, or using ChatGPT. This could be done now. In those days, where there was primitive conditions in ChatGPT, now this could be done in less than a day. But in those days, it took us 2 weeks. So something that would take 2 to 3 years is reduced down to 2 weeks. Okay, well, this is what I want to share with you. I think I like to say that AI is transforming the way we do chemistry in my lab, and we are not looking back at all. And almost all my lab is blending AI and computation into their work and using those cycles that I mentioned. I want to mention that we're trying to commercialize this and accelerate discovery, as I've shown you in the preliminary results. We created a startup called Amatics. You can look it up. I want to acknowledge my wonderful students, the funding agencies and sources, and thank you for the invitation.
Okay, is this live? Yes? Okay, so I should say that I gave my speakers 20 instead of 30 minutes to allow for a question or two in between. I also forgot the most important thing to say, why Omar won all those awards, because he is the inventor of MOFs, COFs in the field of reticular chemistry. Okay, so that's why he won all those awards. Okay, so are there one or two quick questions? Okay,
Thank you. Thank you so much. This was so inspiring. You spoke about the problem of carbon capture and how that's solved, and it's a matter of really society choosing to invest. What are the problems that you see? Is it a policy problem? Is it a matter of funding? Is it a matter of recently I've seen a talk by Tom Chi, and he was talking about surface. So the surface you cover to capture carbon. So are there technical problems? What are these kind of barriers that we have to work on?
We already have plants that capture CO2 out of the air. Just the materials are not very good. The materials break down and they cause problems and so on. They don't cycle as well, right? Because you're pushing a lot of air through the material. So what the problem we solved is that we made robust materials that are going to withstand years and years of cycling without having to replace them or replenish them. So that, I think that's an important advance. I mentioned the comment about society is because when we decide that we have a crisis, like when we did with the pandemic, we put in $1 trillion to fix it, and it got done, okay? And when we decided we had a housing collapse that's throwing our economy out of order, we decided that that's a crisis, and at the time we put in 900 billion, almost another trillion, to put us back in order, and it worked. Well, this one is even better because you're investing in a process that potentially could be a future economy as well. You're adding to our economy by capturing CO2 and everything that goes. Professor Peidong Yang will talk after me, and he will show you that CO2 perhaps could be converted to a high value product. Well, that's another economy. So it is worth the investment. We're not going to be able to do it for free. Okay, you can't just emit for free and capture it for free.
Okay, okay. If you can answer a question in 1 minute, Omar, then
Sure.
we can.
Yeah, sure. So it seems like you're mostly focused on MOFs and COFs. It's sort of adjacent chemistry to zeolites, and it's
It seems like you've experimented with something similar with ZIFs. What was your? Is there any particular reason that you're not focused on zeolites, and do you see any room for zeolites in carbon capture or pure water generation?
No, there's absolutely no room for zeolites because zeolites hold on to water so tightly. You have to heat them up to 300 degrees overnight to remove the water, so that's not economical. For CO2, they're lousy. And the reason we developed MOFs in the mid-1990s was because every zeolite chemist wanted to make zeolites from metal organics. The metal was going to provide them with better catalysis, and the organic was going to provide them with better way of tailoring their pores so they can do very specific reactions. Well, we succeeded in doing that, and that's MOFs. So zeolites are great for refining petroleum, but their days have passed, because now you can make materials precisely by design on the atomic and molecular level, and with the AI, it's unstoppable.
Okay, let us thank Omar again. And Omar also set up our next talk because